muchas gracias a todos por venir. Gracias a IOB Labs que está consolidando esta meetup y nos provee toda la rica comida que vamos a comer después y la bebida que vamos a tomar. Así que muchas gracias. Tenemos dos grandes valores acá de la comunidad, reconocidos internacionalmente. Tenemos a Gaby Kurman, que va a dar una intro de lo que es el ecosistema de RIF, y tenemos a Wojtek, que va a hablar de RIF Storage. Y yo me lo presento. Muchas gracias.
Yo, primero que nada, quería agradecer la invitación por estar acá, por poder presentar lo que estamos construyendo. Muy felices de estar construyéndolo en conjunto con el equipo de Infuy acá en Uruguay. Así que lo primero que quisiera hacer antes de arrancar es felicitar a Infuy por la nueva casa, el crecimiento que han tenido el año pasado a base de ser uno de los mejores proyectos o mejores equipos de laburo en Uruguay. Para nosotros es un placer trabajar con los equipos de Infuy. Así que quiero pedir un muy fuerte aplauso para Infuy, la nueva casa. Gracias por recibirnos. Para mí el crecimiento de Infuy es un reflejo del crecimiento del ecosistema blockchain en Uruguay. Nosotros entendimos el potencial de Uruguay hace un par de años cuando decidimos abrir una pata de desarrollo acá, y cada vez nos convencemos más de que es uno de los lugares donde queremos construir tecnología para el mundo. Así que también Ale y, digamos, todos los miembros de Infuy son parte de esta comunidad que está creciendo, creo que lo estamos viviendo y lo estamos haciendo. Así que también un agradecimiento por armar estos meetups, por abrir las puertas de Infuy a la comunidad. Me parece que está buenísimo y pone muy contento. Respecto de RIF, para los que no conocen, probablemente muchos de ustedes estén trabajando en proyectos de RIF, así que ya saben lo que es esto. Pero para los que no saben, básicamente RSK que permite contratos inteligentes sobre la infraestructura de Bitcoin, ¿no? Y eso nos permite armar un sistema financiero totalmente descentralizado y espectacular. Pero igual hay un montón de componentes de la Internet que siguen estando muy fuertemente centralizadas. El storage, digamos, la mensajería, las redes sociales, los marketplaces. Gran parte de la Internet que conocemos sigue totalmente centralizada y controlada por gobiernos y empresas. Bueno, la visión de RIF Storage es construir estos building blocks necesarios para llevar los mismos beneficios, fortaleza y descentralización del Bitcoin a todas las otras áreas de la Internet que siguen estando centralizadas. Una parte muy importante es Payments, que estamos trabajando con Ale y con el equipo de RSK de IOB de Infuy. Otra parte es el manejo de la identidad, otra parte es la mensajería y otra parte muy fundamental es el storage. Entonces ahora Wojtek nos va a contar cómo funciona este layer que permite almacenar información en forma totalmente descentralizada, permissionless y, digamos, disponible democráticamente para cualquier persona o usuario del planeta. Así que es uno de los componentes principales y muy importantes de esta visión de RIF para construir una Internet descentralizada sobre la infraestructura eléctrica. Así que con esa intro pido un fuerte aplauso para Wojtek. Como la charla va a ser en inglés, si hay alguna parte que ustedes no entienden, quieren preguntar, podemos traducir en español si hay algo que no entienden, ¿ok? Para que entiendan todo.
Hola, ¿es esto loud?
Hi everyone.
Okay. Hi, I'm going to do this in English, even though I'm learning Spanish, but give me a few years. It's not as fast as learning computer languages. So my name is Wojtek, but some people here call me the yellow, the mustard pants. But it's not my fault. It's because this t-shirt doesn't go with anything else. So storage and communications. Today I'm not going to really talk to you about like RIF storage and RIF communications. I want to give you a really understanding why we need decentralized storage, why we need decentralized communications, what are some of the principles that are being applied there, and how such systems can work. Maybe we don't have clicker, right?
No.
No. Okay.
Yeah.
Cool. So the main motivations. Okay, cool. So the main motivations for why we would need such a system is that nowadays the world is more and more decentralized. You're storing more and more stuff digitally. You have more and more documents that even identify you. And in past, you were storing usually most of that on your own computers. Nowadays, we're using mostly cloud. And there's a centralized service providers that are
Sorry.
That's okay. That are creating, that are basically providing the storage capabilities and communication capabilities to third parties. Parties like Amazon, Facebook, Microsoft, they all have their own data centers where they're storing all the data. The problem here is that if you are not compliant with the rules of Facebook, you may get deplatformed. You may lose all your data. You may lose all your identity. So this is one of the things we're trying to tackle with decentralized storage. There's also increasing chance that somebody is going to spy on you, or we all know the NSA leaks. So we need to protect ourselves a bit better. There's a big chance of censorship, even in Czech Republic, which is very, very nice country when it comes to things you can say. I have few times went on a YouTube on a like a video that somebody shared with me, and it just says this video is not available in your country, right? And it was I don't know, something even stupid, nothing that I found worth censoring, but nonetheless it is happening. Another issue is that if you are a developer and you build a website or you build an application that becomes very, very successful, what you need is for it to scale quite well. And in a normal system, this is quite difficult because you need to buy like content delivery networks, and now you need to synchronize between those two. But this is something that actually in a decentralized systems comes usually very free. So the more popular the content becomes, the more geolocalized it also becomes, so you can more easily download it. And the last one is efficiency, and this is not efficiency when it comes to the storage itself or the communication itself. Those are actually usually less efficient. But in a global standpoint, now everyone, even you with your laptop, if you have some spare storage, if you have some spare bandwidth, you can actually provide this storage to third parties. And you can actually make money out of doing this, or offset some of the costs that you had when you were purchasing this device. So, thank you. So decentralized storage, what it is. So we're going to talk about steps that you need to do when you are using decentralized storage. And this is from a user perspective. So what kind of happens? So there's 3 stages. The first one is file preparation. This usually happens locally on your machine. Then there's the uploading of the content, and then usually somebody else would download it. So in the file preparation, I'm going to take Lena, who's going to be my experiment here. So what you usually do is you take a source file, and then you split it into pieces. We call those pieces chunks. Usually it's done on a file level, not on a visual level, but I think this is much more understandable. So we're going to go with this. So you split the input file into pieces that are of some size. Yes. Of course, not always it works well, so you may need to pad this at some zeros or something so that you have uniform sizes of the chunks. And then what you could do is you can encrypt this. And you can do the encryption before or after the chunking. Usually it's done after the chunking because it makes it much more robust. And yes, and then what you usually do is you store these chunks into a structure. One good structure to use is something called Merkle tree. So basically it's a graph, it's a tree, where you have the data and the leaves. And then as you go forward, you actually have a checksums of all the data underneath. And hence verify basically that those chunks are consistent, that nobody tampered with it, and also uniquely identifying those. So this is one way of a tree representation that is usually used. But there are, of course, other possibilities, because this structure is, yes, please, next one, very flexible. So if you, for example, are working with video files and you want to allow for streaming of the video files, you can choose this structure. Because in this structure, it's very easy to search in the video and jump to any given location. So here, all I need to do is I need to download this bit to get these 2 first seconds of the video, and then I progressively download one after time. If I need to actually skip into, like, I don't know, 5th minute of the video, I can just go here, retrieve this, and then I'm already here. This is something that in the balance system would be much more computationally inefficient and quite down. Okay, so that's the preparation. And then in terms of the other actions, so this file preparation is something that the system will usually handle for you completely. But I think it's important to understand so that you understand the caveats, how secure it is. So when it comes to the uploading, you usually are concerned about how the file is distributed in the network and if it's persistent. So if later on you're able to retrieve it. And then when it comes to downloading, you usually care about finding the file first and then how to download it. So I'm going to talk about 2 different storage networks here, mostly because they are very different. Who actually used the decentralized storage here? Is there someone who ever used it? Okay, 2 people. And which ones, if I can ask?
Saya.
Okay. Ale? Saya as well? No, IPFS. Okay, IPFS is smart. I'm going to tell you that most of you actually use decentralized storage. Who used torrents? Okay, torrents is actually decentralized storage, and it works very similar to IPFS. So maybe I'll show you a technology that you've been using and you didn't really know how it works. It's basically this. So it's a set of computers that are connected. They have a peer-to-peer connection, and the files and everything kind of passes through them. So if you want to store a file, what you do is you probably have one instance of the client. So here the IPFS client, and you say, hey, I want to store this file. You upload it there, and that's it in the IPFS system. It just lives there, similar to how you would do it in torrent. Then if somebody else, here the node C, wants to download this file, it basically looks up into something we call DHT, distributed hash table. So this is a hash table which tells you which nodes in the network are storing which files. And it's distributed in the network, so you only have part of this hash table, but you're able to reconstruct it, or you're able to ask your peers to get this table. So here it's very simple. You just find that node B stores this file. So what you do is you contact directly the node B, and the node B sends you the whole file, and now you have the whole file. what's interesting here, and this is something that happens in the torrent network as well, is that the file used to be in just one location. Now it's in 2 locations. So the more popular the file becomes, the more spread in the network becomes. And you can use this to your advantage. So the next time you download a file through some other node, all it needs to do is it actually connects to both of those nodes, and maybe it downloads half of the file from here and half of the file from there, or majority of the file from here, because this guy has a much faster internet connection. And this is where the chunking also comes into play, because you just download by the chunks. And this is, by the way, again, how the BitTorrent network also works. They use something else than the DHT for the finding of the file. But other than that, it's the same. And these providers, these who actually store the files, are called seeders. So they're seeding the file. And then the ones that are downloading it are usually called leeches, because they leech. Okay, but this of course has a few problems. So BitTorrent network is economical miracle, because, and I think it should actually get a Nobel Prize for economics, because even though it's completely free for the end user, it's very popular. And this is because there's such thing as a tit-for-tat protocol and a reputation system. So the most popular uploaders are actually rewarded by their reputation. So they're incentivized to actually share this content. We can't really do that for all the content in the world. So in IPFS, what they are using is similar protocol to the tit-for-tat, something called BitSwap. But their biggest problem is persistence. So how do you prove that you store a file and that you are someone who is providing it to the network? And this is something that is tackling a technology called Filecoin, but that's outside of the scope of what I want to bother you with. But it's a very interesting, and if you're interested in this topic, definitely do read it out. Yes. So the second system I'm going to talk about is Swarm, because the approach is very different. And coincidentally, we're actually integrating those 2 providers into the RIF storage. And it's actually exactly because of that, because the approach is so different, and therefore the use cases are very different. So in the Swarm network, the layout looks completely different. And the connections are not seemingly random as in IPFS. I mean, there is a reason for IPFS to look that way. But in the Swarm, they use something called forwarding Kademlia. So Kademlia connection means that you, let's say this is your computer, you become part of the network, and you have some address, you have some identity. You look at your identity and you compare it to others in the network, and you connect to the ones that are closest in terms of a distance to that. So here it would be the number 2 and F here, because we have 16-ish computers here. So you connect to those 2. You usually have like 8 or 16 close computers in your neighborhood. And then you have at least one connection that is far away. So it's somewhat random, but it basically makes this graph much better connected. So this is very useful for when you're actually trying to upload a file. So in Swarm, there is no such thing as uploading a file to just one node. The file is uploaded to a network. And all the different pieces of the file end up somewhere in the network, and you actually really don't know. I mean, you know, because you know the hash of the pieces of the file, and you know that there must be some computer that's somewhere there, but in reality, you don't really know. So what you do is you upload the first piece into your node. Then looking at the connections, you look at what is the closest node. And here I've chosen it by the prefix. So 2 is the closest connection to 3 that I have. So you contact the node 2. The node 2 then sees that it has a connection to node 3, and it basically forwards there. And the same happens to the next bit. And here we actually see that there's no such thing as node bit number 1, but there's node 0 and 2, and it ends up in either of them, usually in both of them. And the same goes actually even for this file. It usually doesn't end up in just one node, but there's a few nodes storing it with just similar addresses. So yes, one chunk, then a second chunk, the last chunk. Next slide. And now it's somewhere in the network, and you actually don't know if the file exists until you try to download it. So there's no global table through which you could find if files exist. You don't know. And this is really good for anonymity and censorship, because those people that are forwarding the chunks, they actually don't know which file they belong to. They don't know if this is the root, the Merkle tree of the file or not. They actually don't really know anything, rather other than it's coming from this peer and it's supposed to be stored in this direction. That's all they know. So then if you want to download a file, it actually doesn't matter whether you want to download it from the same node or from some other node. But again, the routing is, it looks, okay, I need to find something that starts with 3. So DF is the closest one actually, and then it goes and routes this way. We can see that actually there's a faster way to get the file, and that would be to go this way, right? But this is something that this node doesn't know. This node doesn't know that node B has a much quicker connection. All it knows is that the E is actually closer to it, and it's more probable that it's actually shorter distance. And that's also something very powerful that you can use to your advantage. So you first download the Merkle tree that tells you which chunks you need to download next, and then you can download all of them actually at the same time. So you download the first one, next slide, and you download the last one. Okay. So how do you incentivize this? Because suddenly this is not just a network where only the nodes that would want to store a content would store it. This is a network where everyone participating in the network stores something, and they don't know what they store. And they actually cannot reject storing such thing. I mean, there is a way, but in principle, they cannot. So for downloading the file, we use something called swap. So if you have 2 nodes, you basically just count the chunks as they go until you reach a certain threshold. In this case, it would be 50. And then you basically one node needs to pay the other for all the service that they provide. And this is very nice because you can actually do this as an off-chain payment, so it's very cheap. So the second incentive mechanism would be for uploading file, and this is something called postage stamps. So it's very analogous to how you would use it in a normal mail. Basically, you need to send a letter somewhere. You don't know how it's going to go there anyways. But what you do is you buy a postage stamp of a certain amount and you put it on the letter and it gets there. So the mechanism is the same. You go to a smart contract, you create a number of postage stamps, you put them on your chunk, and you send it to the network. And then the recipient actually gets paid by the postage stamps, and it pays all the notes in between because they use this swap mechanism. And then the last big question is, how do you actually ensure that the files remain in the network? And that's, again, very complex mechanism. It's called Plow and Swindle in the Swarm use case, and I also would not go into that. Partially because I don't really understand it myself that well yet. Okay, so that's for the Swarm. Now, Decentralized Communications. So we already have these two amazing networks. We have IPFS, which is actually a very mature system that has several components. One of them is libp2p, which is a communication network that creates all the connections. Then you have the storage layer itself that actually stores it, and that's called IPFS. And then you have the payment system, which is called Filecoin. In Swarm, you also have a network, which is this Kademlia. You have the storage, and then you have the payment that is on top of smart contract platform. So in communications, what you actually need to do is you need to send message, and you can send it to one person, or you can send it to the group. And those are two use cases you need to have. And you need to receive message, even if you are not online. And this little bit is actually quite difficult. But the sending message is very easy, because in BitTorrent, in IPFS, in Swarm, sending chunks around is sending messages. So if we look at the Swarm network, I want to send a message, I'm a node F, and I want to send a message to node 5. I just say, hey, I want to send this message to node 5, and it gets routed through the network. And you can use the same thing, postage stamps, to actually pay for it as you would in a storage. Next slide, please. So let's say I want to say, hello Montevideo, and I want to send it somewhere. So I can just send it as it is, but I can also use the nice thing, or a nice property of every message, because every message is actually a file. So it's a file, therefore I can create a hash out of it, and I can send it to this node. But what if this node is not someone who wants to receive the message, or it's not addressed to? Well, I can do mining. I can actually say, hey, this is the message, then there's something that separates the rest of the message, and this is just some random data. But each time I add something here, it completely changes the hash of this file. So I can use this to my advantage, and I can just keep adding to the message something that anyways gets thrown away. And I can create a hash of this chunk that would end up in some location of this Swarm graph. And it can get stored there. So this way, basically, communications is the same as storage. Okay, so again, why are we doing this? The current system works. It has flaws though. If everyone is nice and everyone plays well, it's the best system we have, and probably the best system we can have. I mean, centralization is the most efficient way, but it never works. That's the thing. It never works. There's always bad actors that are going to abuse the system. And decentralized storage, decentralized communication, decentralized technologies are the tools that can actually help prevent fraud, help prevent people from doing something that would negatively influence others. Okay, well, that's it from me, guys. Please, if you have any questions. We have some T-shirts for those who ask good questions. All right.
So, how you make the real-time message reality when you have a spread of message? You spread the message in different nodes.
Yes.
So how you send that message to
someone specific?
So someone.
Okay. So yeah, there's two ways. Either you say specifically, I want to send it to this person.
Yeah.
And then it's fine. It just gets routed. But then everyone knows that this message is intended for that person, right?
Yeah.
That's something you don't want to do. A smarter way is you don't send it to a specific person, but you just send it to part of his address. So let's say some prefix of his address. And this gets delivered to everyone who has this prefix. So now it's more people. So you actually cannot identify it as one single person. Sorry? Yeah, basically a broadcast, a limited broadcast. And then if they are smart, as the recipients, even though they know that this is intended for them, and of course it's encrypted, even though they know this is intended for them and they can read it, they still forward it so that they're not identifiable.
Like a message across a MAC a router, a switch.
Exactly. Yeah. Yeah, not new technology. We've already had it. You said it, networks and routing, that's exactly how it works. There first.
Continue this example. I receive a message, okay, and how do I read this message? Because I receive a hash. So how
you actually receive directly already the content.
The content.
Yeah.
Okay.
You receive it directly. But it's some data. So what you do is you try and decrypt it, and if you decrypted it, it's intended for you, basically.
Okay.
I have two questions.
Yeah.
The first, when you show the network, I assume there's more than one node for each letter of the hexadecimal.
Yeah.
How do you manage that? Because you have many C's, many A's, many 2, many 3's.
Right.
And you are going to spread all that on the
yeah. So that's essentially that. So you just have more, and maybe we can go back to that. Yeah, let's say here, right? Yeah, so you're saying you have much more 2's, much more 3's here. Well, you just add a second letter.
Now you have a point of failure.
Yeah, you add a second letter.
Yeah.
So it's 2A, 2B, 2C, etc. And you can go almost indefinite amount. In reality, it's actually this is very simplified. So in reality, you would just have a public key, which is, I don't know, 64 characters of base 64.
Okay.
So a lot of combinations.
But each node, and let's say the 0 node, has to be able to be connected to 2 nodes, because if one goes down, they have to be able to reach the other.
Exactly. Yeah. So you usually connect to some node. We call them boot nodes, and they're usually hard-coded in the code, but you can define them yourself. So let's say you connect to node 2. Your address is, what I don't have, C. And this node 2 actually tells you, well, I don't know C, but I know F.
Exactly.
And until you actually get to know your neighborhood and you connect with everyone you need to connect with.
Okay. Second question is very nice for us that are kind of tech geeks, but what do you think are the most interesting application, real-world application that can be built on top of it?
Yeah. So the easiest one is decentralized websites, especially in this swarm system. You upload something, and it's there. You don't have to pay server fees. You don't have to manage CDN. You don't have to do anything as long as people access it.
Just for static pages.
Just static pages. Of course, you can build databases on top of this, because database is just using file system to store stuff. So you can make a decentralized database, and now you don't need to have a static pages. You actually can have the dynamic ones as well. So that's the easiest one. Then definitely a streaming, video streaming, centralized, basically streaming networks, which can save providers like, let's just say Netflix adopts this. And by the way, Netflix is using IPFS for something. But let's just say Netflix gets this. Well, now they don't have to store all their films. They don't need to pay all the bandwidth to actually serve them, and that's like millions of dollars we're talking here. So yeah, that's a good one. And Netflix is using IPFS specifically for distributing their packages. So software packages, because they just use the hash as a consistency check. So instead of like npm install whatever, you just put the hash in, and it downloads the correct file, and you're sure that it's the right version of the package that has been security checked and everything. So that's another good use case, Git as well. Everything that needs, consistency and immutability.
It sounds like a TV show, Silicon Valley.
Yeah. Pied Piper. Oh yeah, one question.
How does RIF Storage compare to SIA?
So
what are the advantages over SIA?
So RIF Storage is a protocol.
Yeah.
So it basically allows any third party to integrate into the solution, right? So SIA can also be integrated, and right now it comes with the IPFS and Swarm, but it's fully open, and we might integrate some more. We're talking to SIA. In my understanding, SIA is not that well decentralized because and it's actually very much redundant. So in SIA they use the old DVD system, where basically you take a file, you split it, and you create a 10 out of 30 encoding on that, meaning that you only have 10 data chunks and then 20 redundant chunks. So if you lose up to 20 of them, you can still recover the file. And then, similar to how IPFS works, you actually create the contracts directly to a number of providers that are willing to store your data. You define, and this is where SIA is quite ahead actually. So they have this whole mechanism of payment already done. So this is where their strength is. But you create a contract between them, and they store your files. And then from time to time you check if the file is there, or there's a system that checks that. If not, you can reconstruct this one missing chunk that this storage provider no longer stores, and you can contract somebody else to store it. So it's a much more involved system, and but it's quite resilient to the storage providers going offline. Does that answer your question?
Yeah.
Okay.
And another question: do you know how much data is being stored through RIF?
So RIF, it's a tricky question, because you could say that everything that is stored on IPFS and on Swarm is stored on RIF, because we provide access to those. But RIF Storage is a quite new technology, or this protocol. We're actually just now entering the first testnet period, and we're integrating with first few partners, so there isn't much stored. I think we can count it in gigabytes for sure.
So RIF is over Ethereum.
RIF is only on RSK.
It's a network.
Yeah. So this is a layer on top of a smart contract network like RSK. In principle, it's agnostic to the smart contracts, but it has a tight coupling right now with the RSK because we're one organization that is building that. Yes.
Maybe you can explain what RIF Storage adds on top of Swarm and IPFS.
Right. Okay. So with the IPFS, what we are adding is a decentralized way of persistence. So there is a service in IPFS called Piñata. And this is a very centralized system which somebody runs. And what you can do is you can contract them to keep a copy of your files, right? So now they know which files are yours. And if they fail, there's no backup. So what we're building is a decentralized system to this, where you can actually, where anyone can become this Piñata node. Anyone can provide the persistence to your files, and you can have more providers that actually ensure your files. In terms of the Swarm, what we are adding is actually, we're building together with them the incentives layer. So we've built the swap. We're now building the postage stamps, and we're going to build the Swear and Swindle as well. And right now we have two separate networks, the Swarm on Ethereum and the Swarm on RIF for RSK. But the overall goal is to unify those two networks because it doesn't make sense for those networks to be separate. I mean, payment is agnostic or storage is agnostic to payments. It doesn't matter how you pay for the storage, but having a unified network with more providers and more options actually makes a lot of sense. And it adds, it's like Bitcoin mining, right? If you only had networks of Bitcoins where there's only a few miners here and there, it probably wouldn't hold this value it holds now.
There is a question in Zoom.
Okay.
Oh,
right. What do you think about Storage, and which would be the most important differences between RIF and Storage? So I have to admit, I'm not an expert on Storage. The research has been done mostly by our research team. So I would refer to them for answering the question. But as far as I understand, Storage at first was building their own decentralized storage system. And I might be completely wrong here. I'm sorry, but I want to provide some answer. But they've been building their own storage system, which since has been somewhat abandoned. And now they're more focused on a cloud storage system using a decentralized storage system, but managing it kind of more as a cloud component, so different companies can integrate with that.
Sure.
Any more questions here or there?
No, as far as I can see. No.
Dos pequeños
Ahora la pregunta. Es una pregunta.
Yeah, this one definitely. Yeah. I think we go there.
Thank you.
Yes. All right. Yeah.
Dos pequeños anuncios. Primero, hace un ratito se acercó Manu, que no sé si lo conocen, el co-founder de un proyecto que se llama Money Exchange, que es una stablecoin sobre Bitcoin. La idea es hacer una meetup la semana que viene sobre un workshop de cómo usar la plataforma de ellos. Probablemente también con Luminous o algo de eso, alguna demo. Cualquiera que quiera presentar charlas, siempre es bienvenido. Cualquiera que quiera, los incentivamos a usar RIF, RCK, les podemos ayudar. Y si son de otras tecnologías, también la Meetup está abierta para cualquier tecnología, pero si se quieren acercar a RIF o RCK, pueden contar con nuestro apoyo, después pueden venir acá a presentar libremente. En el fondo hay comida, bebida, para los alcohólicos y no alcohólicos. O sea, bueno, muchas gracias por venir.